Hey everybody, welcome back to another round of physics, and yeah, let's get going. I thought that I would put up an example video here of applying KCL and KVL to capacitive networks. And we'll see that although we tend to say the word current law, we could apply the same idea when we're dealing with individual charges. And so, although we could address this network shown for you in terms of combining capacitors in series and parallel, I will opt to do it in an alternative method, namely using Kirchhoff's laws. So go ahead, take a minute, go through, pause the video, and start running through the series of steps to sort of get the circuit ready for us to write down our equations. You got it? Yeah, good. Okay, so we'll go off running like a bale of turtles. I'll go ahead and use cyan. So we have our 9-volt battery down here. So I'm going to go ahead and say that the current from that 9-volt battery, I think I'll just call it I naught here. We'll say that it's going as indicated here. Well, if it's doing that, then I assume that the current here is I40. Okay. And I should say, of course, when these capacitors are fully charged, there is no current anymore. So I'm thinking about the direction that the current was flowing in order to have charged up the capacitors. And similarly, I guess I'll go ahead and say this way. So I don't even know what to call that. I guess I'll call it I60 here. And 60 because you have current flowing through the 10 ohm or 10 microfarad resistor. You have current flowing to the 20 microfarad resistor. And then of course, instead of 60, I think I'm going to call this 30 instead, because this current right here will be the same as the current flowing right here. Okay. So yeah, it's always good to make sure that you don't accidentally put in an extra current where it doesn't belong, because then you'll accidentally look for additional equations. You'll think you have more unknowns than what you actually do. So just be careful on that. So good. So what we see here, let's see, we have the current flowing through that branch. We have the current flowing through that. Yeah, it looks like we have 1, 2, 3, 4, 5 unknown currents. So we have 5 unknowns, which means we need to go ahead and find 5 equations in order to solve for those unknowns. Okay. Last thing, we should label based on the direction that we've put down. We should label the high and low sides of each of the capacitors and the battery. So we'll go ahead. This is the high, that's the low, high, low. Hi ho, hi ho. There we are. Okay. So now, before we go about applying Kirchhoff's current law, we should make sure that we label the nodes. And as we talked about last time in our resistive network circuit, we have a node indicated right here in green and a second node. And because they are connected by a perfect wire, these two nodes are actually the same. You can imagine shrinking that perfect wire down to 0 until that location of the circuit connects with this location. Okay, so I'll go ahead. I'll call that node A. We have a second one right here, which we'll call node B, and then a third one right here, node C. Okay. And notice that there's a circuit element between any of those nodes. So they're definitely different. Okay, well, let's go about applying KCL. And heck, just to be different, let's go ahead and apply it to junction B. And so we remember that KCL technically tells us that the current in should be equal to the current out. Okay. But for capacitors, when everything's fully charged, there isn't any current flowing anymore, right? Like the capacitance gets full and then it acts like a break in the circuit. But we'll still apply the same idea. What we'll say is the total charge that has entered that junction must be equal to the total amount of charge that exits. And so now we can go through and we say, okay, well, we have, for example, the charge on the 20 farad capacitor. that's going into the junction. So I'll say, the total amount of charge on the 20 farad capacitor. You have the total amount of charge that was on the 10 farad capacitor, and that must equal the total amount of charge that exited the junction, i.e. the total amount of charge that ended up on the 30 farad capacitor. So there's one equation. Okay. Why don't we go ahead, let's do a second equation. Let's look at junction C as in cat. Okay. Yeah, and hopefully you see again, the ins, that would be the charge from the 30 farad capacitor plus the charge from the 40 farad capacitor. That must equal the amount of charge that went to the battery. I guess I'll put Q battery here. Okay. Good? All right, good. So there's our second equation. And now because we have 3 junctions, we know that we can only use 2 in order to derive equations. And so now we must go and start looking at KVL, the loop rule, in order to find the rest of the equations. Now, for purposes here, we could choose any of these. I think what I'll do is let me go ahead and choose, I think I called it last time, I said, let me choose the top loop. In other words, the one that involves the 10 and 20 microfarad capacitors. So we'll do the top loop. I don't know, let's go ahead and do the bottom loop here. And I don't know, fielder's choice. What do you want to do for the third? Let's go the inside loop. So we'll use the top loop, we'll use the middle loop, and we'll use the bottom loop. Okay. So why don't we go ahead and write those 3 down. Let me go back to green so it's a little more visible. So now we're thinking about using KVL. So KVL. And let's start with that top loop. And here KVL tells us the sum of the jumps is equal to the sum of the drops. And so we choose a starting spot, I'll say right here, and we'll walk, and we notice that we have a drop across the 10 farad capacitor. So I'll put V10 here. And we keep going, and we keep going, and we notice that we have a jump across the 20 farad capacitor. So I'll put V20 here. Okay. Well, very good. Of course, now we will go ahead and substitute in the relationship between the charge on the capacitor and the potential drop across the capacitor. Namely, that V across the capacitor is equal to Q divided by C. So in this case, we have the charge on the 20 microfarad capacitor divided by its capacitance must be equal to the charge on the 10 farad capacitor divided by its capacitance. And we'll go ahead and call that equation 3. Now similarly, go ahead, for the middle loop. Right, I'll go ahead and walk clockwise. Let me start at B. I've got a drop across the 30. So I've got V drop. I've got a jump across the 40, so I got V40. And then I keep going, and you notice I have a drop across the 20. So 20 drop, 30 drop equals the 40. And so the fourth equation that I will get says the charge on the 40 farad capacitor, microfarad, is equal to the charge on the 30 microfarad capacitor plus Q20 divided by the capacitance of the 20 microfarad capacitor. There's number 4. And last but not least, we'll see if we can squeeze it in here. We've got the bottom loop. And the bottom loop, again, we see there's 2 elements. I'll start at A. We have a drop across the 40 microfarad capacitor and a jump across the 9-volt battery. Or, since we have V battery is equal to the charge on the 40 divided by the capacitance of the 40. We'll call that equation 5. Now again, we'll have to sit back and ask ourselves, is there easy ways to combine these 5 equations to get all of the answers that we want or that we need? Technically, I have 5 equations, 5 unknowns. I should now be done with the problem. Now we'll go ahead and look, but for example, equation 5, we recognize that we immediately have enough information to solve equation 5 for the charge on the 40 microfarad capacitor. We have the voltage, the potential of the battery. We have the capacitance. Boom. We can just put in the numbers. So let's go ahead and do that. We have so thinking about equation 5, we said that the battery was 9 volts, and that's equal to the charge divided by 40 microfarads. Okay? And so multiplying those two together, we get 360. Now be careful, I have micro here, so I'll leave the micro, and we have microcoulombs is the amount of charge stored on the 40 microfarad capacitor. So let's go ahead and box that one. That's fine. Okay. Now we have used that equation, so let's go ahead and just indicate, okay, don't use this one again. We've already got that one taken care of. Okay. And so now, again, we have to take a step back and we have to say, okay, well, is there any easy way for us to start subbing stuff together in order to simplify? And, truth be told, I have zero idea. So let's see here. So I put that in there, I put that in there. No, I can move that over here. I don't really see anything that would immediately jump out at me. And so I think probably what we need to do at this point is start just being very intentional. Namely, let's say which item, which charge do we want to find next, and then kind of focus our attention on getting just that charge in all of the equations. So the one that jumps out at me is, let's see here. I think let's go after maybe the 30. I think let's go after the charge on the 30 microfarad capacitor. Now, why I chose that one, if I look at equation 3 tells me the charge of the 20 and the charge on the 10 are related. And so if I look at 1, I see 20 and 10 again. So I can substitute 3 into 1 to get a relationship between the charge on the 20 microfarad capacitor and the 30 microfarad capacitor. Okay. Good. Then I say, okay, I can take that equation and substitute it into equation 4, where there's a relationship between the 30 and the 20 microfarad capacitors. And that will allow me to just get the charge on the 30 microfarad capacitor. So give me just a brief moment. I'll go ahead. What we're going to do is we're going to sub equation 1 into equation 3 and solve for Q20 in terms of Q30. Then we're going to take that result and then we're going to sub into equation 4 to solve for Q30 in terms of Q40. And because we already know the value of Q40, that will tell us what the value of Q30 is. Okay? We will go ahead. Equation 1 can be rearranged to say Q20 times C10 over C20 is equal to Q10. Okay? And then equation 3, we can say, equation 3, excuse me. Strike that, reverse it. We're going to sub equation 3 into equation 1. Here we go. Sorry, I got that backwards. So this is equation 3. Okay. So equation 1 tells us Q20 plus Q10 equals Q30. But now from rearranging equation 3, I have an expression for Q10. So I can write Q20 plus Q20. Now, 10 microfarads divided by 20 microfarads, that gives us 1/2 is equal to Q30. Or, if you prefer, 3/2 Q20 equals Q30. Or Q20 is equal to 2/3 of Q30. So now we have, as I said, we have solved for Q20 in terms of Q30. Now we're going to go ahead and equation 4, right here, tells us how Q30 and Q20 are related to Q40. So now we have, from equation 4, we have Q40 over C40 equals Q30 over C30 plus Q20 over C20. Let's make sure I got that right. Okay. And we can take this result and substitute it in for Q20. I'll go ahead, I'll put in the 40s, that kind of thing. But what we have here is we have 360 microcoulombs divided by 40 microfarads equals Q30 over 30 microfarads plus 2/3 Q30 over 20 microfarads. And again, I'm just leaving those units in there just to remind ourselves that we were dealing with those microfarads. Okay, so it's a non-SI unit, right? It's got that prefix on there. It's always good to just keep it in there. But what we see here is that indeed there's only one unknown in this equation. We can finally solve that for Q30. So let's go ahead. Let's take a moment and do that. Of course, 360 divided by 40 is 9. So yeah, it's okay. So we get 9 is equal to the charge 30, 1 over 30 microfarads, plus 2/3, 1 over 20 microfarads. Of course, we have a goody-goody moment, right? Like that 2 cancels this, and that gives us 10. And 3 times 10 is 30, right? So it's always nice. We have 9 is equal to Q30 times, I don't know, 1/30 plus 1/30 is 1/15. So we get this. Or if you prefer, let's see, this 9 times 15. So that's 135. So we get 135 microcoulombs equals Q30. Okay. The micro again coming from here, and then this is a farad. It turns out this is a volt, so farad times a volt is a coulomb. And there is our result for Q30. Ta-da! Of course, now, because of some of the stuff that we did, at one point we had a relationship. We had something like Q20 is equal to 2/3 Q30. But now that we have a charge for Q30, we can now find Q20. Q20 is equal to 2/3 times 135. Is 135 divisible by 3? Well, let's see. 1 plus 3 plus 5 is 9. 9 is divisible by 3, so 135 is divisible by 3. Okay. Duh. Hi, my name's Greg. It's 45. So this gives us 90. Oh, excuse me, that Q3 doesn't belong there. So this gives us 90, right? 135 divided by 3 is 45, times 2 is 90. So the charge Q20 is simply 90 microcoulombs. But wait, there's more, right? We had a relationship that related Q20 to Q10, right? In fact, recollection is that we got that Q10 was 1/2 of Q20, right here. So we also have that Q10 is equal to 1/2 Q20, and therefore Q10 is equal to 45 microcoulombs. So, if I recall correctly, we have found the charges on all the capacitors. The only thing that we have left to find is how much charge how much charge left the positive terminal of the battery and returned to the negative terminal. And so the last equation that we need to use is probably, here we are. We have the Q40 plus the Q30 is equal to the Q of the battery. Well, Q40 was 360. Q30 was 135. And so we had Q40 plus Q30 equals Q of the battery. And so we have 360 plus 135 is equal to the amount of charge that left the positive terminal of the battery and returned to the negative terminal. And so we see that this is 495 microcoulombs. Boom. Ta-da. Cool, right? Now, please bear in mind, that solves everything that we need to know about the circuit. Okay. Now we know exactly how much charge is stored on each of the capacitors, or conversely, we know how much potential or the change in electric potential across each of those capacitors. Please remember, the change in electric potential across the capacitor is just simply the charge divided by the capacitance. So by knowing the charge, we can immediately determine the change in potential across each of those capacitors, and that allows us to solve the entire circuit. They're completely synonymous. You either know all of the charges, or you can use the charges to find the potential drops. Just like in the resistive networks, we were able to use the currents to figure out the changes in potential across each of the resistors. So I think that's it for you, at least in this episode. But I guess the underlying idea is that Kirchhoff's current law, Kirchhoff's voltage law are just as applicable to, say, a network consisting of capacitors, just as much as you could do for a network consisting of resistors. What we will now see, or at least in future videos, is that we can also do it for networks that contain both resistors and capacitors. And in those types of circuits, we will find that we're forced to look at the time-varying nature of the circuit. So we'll leave that for the next episode. I thank you for your hard work and your attention. Keep up the good work. I'll see you next time.